So we resume. So I said for the people on Zoom who couldn't hear my sort of preamble to the mini course that I would begin with a kind of general introduction to how the wonderful compactification came to be developed and studied, and its origins in algebraic geometry, which is where most of the things that we understand about it come from. So to do this, I'll start with H, a complex algebraic group. So you can imagine that H is any familiar group like GLN over the complex numbers, or SLN over the complex numbers, or a complex torus, or an additive abelian group that's just a product of n copies of the complex numbers. The basic object that we're interested in is going to be an algebraic variety. Which I'll denote by X circle, with an action of H. Which has the property that it's a homogeneous space. So this means that this action is transitive. And in this case, we can identify X with a quotient H mod some subgroup K, where K is just a stabilizer of a given point. And then we'll say that an equivariant compactification of X circle is, what I want to say, variety X with an action of H that has the property that it's projective. So projective means that it lives as an algebraic closed subset of some projective space. And
what is X? Like, what's capital X in that?
Sorry. It's capital X circle. Yeah. So I want to denote homogeneous spaces with these circles because I will denote the kind of compactifications without the circles. This is the plan for the notation. So an equivariant compactification of such a homogeneous space is a larger algebraic variety that is now projective into which my homogeneous space embeds as an open dense H orbit. So I have an algebraic homogeneous space. I have an action of the group on the space which is transitive, and then I can embed the space in principle as an open dense orbit into various larger spaces, and I'm going to consider those that are projective. So in the real sense compact, yes. Yes, so whenever I say open closed, I mean Zariski open, Zariski closed. Yes.
What is the H for what?
What is the
H for what?
H variety just means a variety with an action of H. One more question. Yes.
Can you just recall briefly, like, what's the algebraic variety and what's an action? Like,
yeah. Yes. So if you want a model to think of algebraic varieties, you should think of them as closed subsets cut out by polynomials in C to the n or in projective space. And when we cut out things by polynomials in projective space, then they have to be homogeneous polynomials for the cutting out to make sense. And this defines a topology, which is called the Zariski topology. And I want kind of everything that's going on the board to respect this topology. So when I have an algebraic group, this means that it's a group, but also an algebraic variety. And the group multiplication and the algebraic structure should be compatible in the sense that the group multiplication is a morphism. And when I have an algebraic group acting on an algebraic variety, then I want the action map to be an algebraic map and so on. Okay. So I will try, my plan is to kind of try not to say anything that essentially involves any very technical algebraic geometry or representation theory in this course, and instead try to give you like a kind of overview with specifics that are more kind of Poisson related. And it's very good if you ask these questions, because then I can at least give some impression of where the details are. Okay, so we have these homogeneous spaces. We're interested in understanding their compactifications and the kind of general problem or the general family of questions that you can ask about such equivariant compactifications is, can we classify? So can we classify all equivariant compactifications of a given homogeneous space? So of course, this is a very ambitious question, and in general, you'd expect the answer to a question like this to be no. But if we restrict to maybe particular examples of homogeneous spaces or particular examples of groups H, then the answer might be closer to a yes. So one example that may be familiar to some of you is the example in which H is an algebraic torus. And in this case, for any homogeneous H space X circle, equivariant compactifications are a subset of the class known as toric varieties. These are varieties with an open dense action of an algebraic torus. And the smooth ones, at least, are classified by a combinatorial object known as a fan. So again, if this is something that you've seen before, are familiar with, then this is a good example. And if not, I'm not going to give details about it because we won't use any of the structure theory. But the moral being that if we start with a very simple group, then we might be able to understand all of these equivariant compactifications using some kind of like simple combinatorial object that we can easily extract data from. And in this case, a fan literally looks like I draw some cones in the plane, and those cones are indexing what do the torus orbits on a compactification look like, which orbits are in the closures of which other orbits, and things like this. Okay. I welcome questions at this point, so if there are more questions, please ask. Yes.
I assume that H only acts on X, doesn't act on the unknown space.
Yes, it does not. Okay, so of course algebraic tori are a very sort of particular and very nice example of algebraic groups. What we can try to do is enlarge the class of groups that we consider for this question if we at the same time maybe restrict the class of homogeneous spaces that we're asking it about. So from now on, I'll always assume that H is reductive. Reductive means that all representations decompose completely into a sum of irreducible representations. GLN is still here, SLN is here, 4i are here. And in the case of reductive groups, I restrict myself to considering homogeneous spaces which fall into a class that is called symmetric spaces. So we'll say that a homogeneous space X is a symmetric space if there's an algebraic involutive group homomorphism, so an involution sigma from H to H, which squares to the identity, such that K is the fixed point set of this involution. So let me give one example. To show you that kind of these symmetric spaces at least contain some large class of homogeneous spaces for the group. So suppose that H is a product of two copies of some group G, and consider the involution sigma, which flips the two copies. So in this case, the fixed point set H sigma is just the diagonal subgroup of pairs G comma G with G and the factor big G. And in fact, if I consider the map that goes from G cross G to G, that takes a pair GH to G multiplied by H inverse, this is a surjective map. And its kernel is exactly, maybe I don't want to write this, it's not. And its kernel is exactly the diagonal elements. Which means that we can obtain the group G as a quotient of our H modulo this diagonal subgroup. So what did we show? We showed that every group is in fact a symmetric space with respect to this flipping involution. Let me pause again for question.
So is H sigma mean which on the dimensions that sigma x equals to?
Yeah, thank you. This means points in H with the property that they are fixed by sigma. No more question. Yes. Yes, usually I said it, but I didn't write it. I wanted to be a homomorphism, and in this case, I also wanted to be an algebraic map. Mhm.
So given any group G, there's also an evolution which sends every element to its neighbors.
Yeah. Yes, but that's not a group homomorphism.
Okay, yeah, right.
But yes. Okay. Okay. So here's so at some point in I think the early 1980s, two Italian mathematicians, Concini and Procesi, showed that every symmetric space of a particular type of group whose center is trivial. So this is the center elements H and H that commute with everything. But under this assumption that our group H has trivial center, any symmetric space X circle has something called a wonderful compactification. So in the statement of this theorem, I will embed the definition of what this means. It's an equivariant compactification X that has the following three properties. It's smooth. Principal algebraic varieties can be singular. If I look at the complement of the open dense orbit given by the homogeneous space X circle, this is a divisor whose irreducible components I list. And this divisor has simple normal crossings. What does this mean? It means that each of these irreducible components is smooth. And when I look at them locally, they look like a union of coordinate hyperplanes in Euclidean space. And because I have an action of the group H on X, and also an action of the group H on this open dense orbit, means that H also acts on this complement boundary divisor. And the H orbits on this boundary divisor are indexed by subsets of its irreducible components, in the sense that if I take the orbit indexed by J and take its closure, I get the intersection of all the corresponding divisor components. So this is an equivariant compactification of this X circle, where X circle is an open dense orbit. And then the boundary of the compactification is a union of finitely many orbits. And the big ones have closure of codimension 1, are these irreducible divisor components. And when I intersect the irreducible divisor components, I get kind of more and more examples of smaller orbit closures. Question, yes. Yes, so really I should have said that the real definition is that it's a symmetric space, so it's an open subgroup of this fixed point group, so it contains the identity component and is contained in H sigma. But since I'm not going to need that anywhere, and I want to kind of sweep details under the rug. Yes, yes.
Do you require that sigma is an homomorphism?
Yes, I require that sigma is a homomorphism and also algebraic homomorphism.
And in the statement of the term X is projected.
Yes, because it's an equivariant compactification. So I am only going to consider these equivariant spaces that are projected. In general, people also consider kind of equivariant embeddings into larger spaces that are not projective, but this is somehow tangential to what we're talking about. More questions? Yes. Let me draw a picture. So here's a picture of a plane. That's going to contain a simple normal crossing divisor that will be the coordinate axes. And these will intersect in this pink point. And what you can imagine the statement is saying is that I have a group action on this plane, so that one orbit is made up of the complement of this divisor, and then each line remove the origin is another orbit, and when I take their intersection, I get a kind of unique closed orbit, which is this origin point. So we can actually immediately draw some conclusions from the statement of this theorem. For example, we can say that there's a unique closed orbit of minimal dimension, which is just going to be the intersection of all of the hyperplane, the irreducible hyperplanes in the divisor, hypersurfaces. And we can also see that because this is a divisor with simple normal crossings, all the intersections of its irreducible components are smooth submanifolds of this X. So in particular, this tells us that orbit closures are smooth because they are given by these transverse intersections. Mm-hmm.
And the orbits themselves, do you obtain by taking orbit closure and taking...
Exactly. So you can reconstitute the orbits by just taking, there's like a partial ordering on the subsets of this indexing set, and you just kind of remove the smallest layers at every step, and in this way you get the orbits back. No, this is I said this was the bijection, so it's like this. I'm assuming that this is in particular non-empty.
Is that what you asked for, or is there any result involved?
There's
If there is any result involved, or you just assume that to be non-empty?
So definitely, it's the case that I need to have at least one closed orbit, right? In anything like this. You should take these 3 bullet points as being part of the definition of what wonderful compactification means. And this theorem telling you that something that satisfies this definition exists. But in principle, of course, I could have kind of, you can imagine sort of like arrangements of hyperplanes in the plane, where if I take the intersection of all the hyperplanes, I get something that is empty. Mm-hmm.
So, is the Tory variety a wonderful complication of C star?
It's not. And the reason for this, so this is a good question. The observation is that these properties that I've listed are really like very restrictive. Like these conditions on the orbit closures, for example, are not easy to satisfy. And in fact, there are examples of homogeneous spaces, of symmetric space, and of groups. So what do I want to say? A remark. Not all homogeneous spaces have such a compactification. So it's an exercise in algebraic geometry that is not very hard, but also not trivial, to show that if you're familiar with toric varieties, for example, if I have a projective toric variety with a unique closed orbit, it's a point. So in general, for example, toric varieties will fail some of the defining properties of this compactification. And I think historically, once this theorem was proved, people really started to ask themselves, why is it that this class of symmetric spaces has this nice type of compactification, whereas there are many, many examples of symmetric spaces for other groups that fail to have such a thing? And what is it about these things that distinguishes them? And that's kind of led to a broader classification program for equivariant compactifications. Okay. Yes.
Just the same thing about canonical or unique, or
I want to say that in a little bit. So I want to give kind of a bit more a bit more of this kind of impressionistic story for where this compactification fits in and why we would expect it to arise. And then we will kind of draw a line and start from scratch, and I will give concrete definitions and an example of this. So let me make a definition to give some idea of what kinds of homogeneous spaces we might expect to have this kind of compactification. So these are called spherical spaces. We'll say that a homogeneous space of H is spherical if a maximal connected solvable subgroup of H acts on the space with an open dense orbit. So let me give you an example that might be somewhat familiar of when something like this is the case. Suppose that so far our running example of a symmetric space is the group itself. So I take H to be G cross G, and inside G, I take a Borel subgroup. So if you think of my group as being GLN or SLN, this is the subgroup of upper triangular matrices. And this, all maximal connected solvable subgroups of GLN are conjugate to this subgroup. And then the corresponding subgroup of G cross G is B cross B. And thus acts on the group G viewed as a quotient of G cross G just by left and right multiplication. So when I apply G comma H to A, I get G A H inverse. And there's a theorem known as the Bruja decomposition that tells us that I can take my group G and decompose it into a disjoint union of B cross B cosets, which are indexed by the Weil group. So this is a finite union of two-sided cosets of the group B. And inside it, I have, maybe I didn't. Inside it, I have an open dense piece that is the Bruja coset of maximal dimension that's usually denoted by this indexing W naught, which is the longest element of the Weil group, and this is open and dense. So in this way, you can see that our first example of a symmetric space satisfies this property of being spherical, because I can use this decomposition into finitely many B cross B orbits of the group G to show that one is open and dense. Let me give a second example. In the case where H is an algebraic torus, this is an abelian group. So in particular, it is itself solvable. Solvable just means that the series of derived subgroups terminates finitely many steps. So this is itself solvable, which means that all of its homogeneous spaces are spherical because they're all just single orbits of the solvable group. So all toric varieties are spherical in this sense. And if you want to do a bit more work, you could show that in fact all symmetric spaces are spherical. And there's a theorem due to Luna and Wust, which tells us that any homogeneous space let me write. Any homogeneous space, X circle, which has a wonderful compactification. So a compactification which satisfies these three properties is a spherical space. I actually don't know. I tried to Google this and there's a question on Math Overflow why are spherical spaces called spherical and no one had an answer. So I don't know. So I don't know. There are a lot of conjectures. People think that it doesn't have anything to do with spheres. I don't know. Okay, and this theorem was kind of part of a larger program initiated by these two people whose goal was to classify all equivariant compactifications of spherical spaces. So this is, I think this program came to be known as Luna-Boost theory. And its goal is to classify all equivariant compactifications, or even more generally, equivariant embeddings into spaces which are not necessarily compact of spherical spaces. And over C, this has really been done, and the classification is again in terms of some combinatorial data, very similar to toric varieties, except with extra structure. So I think instead of fans, they're known as colored fans. And in this classification of compactifications of spherical spaces, there are two kind of very special subclasses of equivariant compactifications. So two distinguished classes. One is a class of toroidal compactifications. And this is a family of compactifications that you can think of as having very big boundaries. So locally, these spaces look like toric varieties. They're described by fans. The boundary is a simple normal crossings divisor. Maybe, I don't know if I want to say simple. Simple normal crossings divisor. And they have the property that any equivariant compactification of a given space is dominated by a toroidal one. So for any equivariant compactification of X, let's call it X, of X circle, there exists a toroidal compactification X prime with a proper equivariant map to X that restricts to the identity map on the open dense piece that is the homogeneous space X circle. And this sort of dominating toroidal compactification you can obtain by taking a compactification which is not toroidal and just doing a sequence of blowups until you obtain, I haven't given a definition of what toroidal means, but until you obtain something toroidal. So in particular, until you obtain a normal crossings boundary. So you can think of this as being the class of like really big compactifications of this homogeneous space where the boundary divisor is kind of as large as possible. Mm-hmm.
Sorry, I asked a question.
Yeah.
So what is the example? I mean, so what is the wonderful or one of the wonderful compactification of C star n?
Yes. So C star n is not going to have any wonderful compactification because any compactification of C star n is a toric variety. And these just can't have compactifications with a single closed orbit. We will see an example of some compactifications. I promise. I will give an explicit construction with formulas, and then we will have examples. This is hopefully I'll even be able to do it today. Yeah. So.
Can you say something more about what you need to be locally categorical?
Yeah, so that's really not clear because right, the group H is not a torus, but somehow it contains tori. So I would like to like pick a point and find an open subset that looks like a product of just an affine space times a variety that is toric for some good torus of. I don't want to say details, except that you can ask toric with respect to what torus, and I will say with some distinguished torus in H that is determined by the point. Okay, so I've had two distinguished classes of compactification. One, the class of toroidal compactification. One, the class of simple compactification.
These 2 points are just describing those.
Yeah. Yes. They should have been dashes, right? In my formatting of. Yeah. I'm describing toroidal compactifications. Second class, sort of distinguished compactifications of these spherical spaces are called simple compactifications. And all that means is these are compactifications that have a unique closed orbit. But as we've seen, these may not exist. So these simple compactifications are kind of the ones with the smallest boundary, but a homogeneous space may or may not have one. When it does, when X circle has compactifications with this property of having a unique closed orbit, then there's a unique one which is also toroidal. So you can think of this as sitting in a kind of picture where I take all possible equivariant compactifications in my homogeneous space and I order them by dominance. So if I have a proper map from one to the other, then they're in an ordering relation. And the toroidal ones are the ones that are kind of big. And the simple ones are the ones that are small. Of which there might not be any. But if there are some, then there's exactly one that is in the intersection of these two classes. Which we'll call X. And if it is a smooth variety, there are various criteria that have been developed to check when a space has simple compactifications when its simple compactifications are smooth. If X is smooth, then it is wonderful. So it satisfies these three properties that were previously on the board. And if this wonderful compactification exists, then it's going to have the following universal property. That if I take any toroidal compactification X prime, and any simple compactification X double prime, the map, the proper map from X prime to X double prime is going to factor through this wonderful space. On the open dense copy of X circle in each of these guys, it's just going to restrict to the identity map. Is it always? Yes, there's always a map from the toroidal to the simple one, and it always factors through this wonderful compactification. Because, yes, so I don't think any of these things are obvious, but this tells you some sense in which this wonderful compactification is canonical, in the sense that it has sort of a large normal crossings boundary like we saw, but it's kind of minimal among compactifications with that kind of boundary. And it also has, in some sense, a small boundary because it has a unique closed orbit, but it's maximal among compactifications with a single closed orbit.
So projective toric variety says that it's in the upper thing, right?
Yes. So if H is a torus, then projective toric varieties live up here, but down here there's the empty set because there are no simple compactifications of a torus.
This means that it has
Yes.
a unique closed orbit, or
Yes, this is actually a definition, unlike the other dashes. Yes. Yes. So I should say, I didn't write very many words here. I should say for any toroidal compactification X prime, for any simple compactification X double prime, there exists proper variant maps from X prime to X and from X to X double prime that restrict to the identity on the open dense copy of the homogeneous space. More questions?
Is anything that is wonderful in the intersection?
Is anything?
Is wonderful.
There's only one wonderful thing. Yes. So this is. Yeah. So there's really a unique. I think the way the proof of the statement goes is you show that if there are simple compactifications, then there's a maximal one that dominates all the other simple ones. And then you show that that one is also toroidal. So this intersection really contains only one point. No more question. Okay, so this has been kind of the narrative of how wonderful compactifications came to be studied. And now in the last, how much time do I have? 5 minutes. Okay, in the last 5 minutes, I will give you a concrete construction of how you would even produce such a compactification in the case of a group, so currently our favorite symmetric space. And then tomorrow, we'll study its structure. So from now on, I will take G to be, like I said, still a reductive group over C with trivial center. So what you can imagine is that this group is PGLN. I take the favorite reductive group, like the general linear group or the special linear group, and I mod out by the center, and what I'm left with is this group of projectivized invertible n by n matrices. And I'll take T in G to be a maximal torus. And I'll take G tilde to be the simply connected cover of G. So if you're thinking that G is PGLN, then you can think that G tilde is SLN. And then from representation theory, we know that irreducible representations of G tilde are indexed by dominant weights of its maximal torus. And if you think, like, for example, in the case of SL3, you have a kind of two-dimensional lattice of weights that are broken up into vial chambers on which the vial group is acting by some reflections. And we pick one of these chambers to be dominant. And we're going to say that an irreducible representation is regular if its corresponding dominant weight lies in the interior of the dominant chamber. So on my picture, the dominant chamber is this cone. And its interior are all of the things that are not on the walls. And these interior elements are the regular ones. So if we pick such a representation, let's call it V, then we can construct the following diagram. I have my simply connected cover G tilde, and because it's acting on the vector space V, I have a representation map that maps G tilde into endomorphisms of V. And in fact, this map, because these endomorphisms are always invertible, lands always away from 0. And then I can do two things. On the left, I can quotient the simply connected cover by the center to get the group G that has trivial center. And on the right, I can quotient this vector space excluding the origin by scalars. And I'll get some projectivized endomorphism space. And because G has trivial center, and because I pick this irreducible representation to be regular, this representation map up here descends to a map from G into this projectivized endomorphism space, which is actually injective. And the wonderful compactification of the group G, you can take this as a definition, is the closure of the image of this embedding, which we denote by G bar. What we've done in order to produce this compactification is we've taken the group G, we've embedded it into a projective space, and then we've just taken the closure, and this automatically gives us a projective variety in which G is sitting as an open dense subset. So examples and interesting associated Poisson structures to come tomorrow.
Okay, thank you. Questions? Don't be shy.
Or the simple example, PGL to C.
Yes.
Is it easy to describe what you want
Yes.
to do?
So but I was out of time, so I didn't do it. But I will do it tomorrow. So in that case, this embedding is actually just an embedding into projectivized 2x2 matrices, and the wonderful compactification is the copy of P3. But we'll see immediately after we do this tomorrow that this example doesn't generalize. So it's not like for PGLN, I'm just embedding here into n squared minus 1 dimensional projective space and then taking the closure.
Any other questions?
Where is the regularity question there? Like, how are you using the fact of the representation?
To show that this representation map descends here, and I didn't write any proofs, so it's a bit short on the details, but this is where you need the regularity assumption and also the trivial center assumption, because otherwise you may get a map that that doesn't descend, or that descends to something that's not an embedding.
Going back to my earlier question.
Yes.
So this one of the terms that gave for symmetric spaces
Mhm.
unique or not?
Yes, it's unique with this property, that it's the unique compactification of the symmetric space that has a unique closed orbit and is also toroidal, which is the term I didn't define.
Oh, but if you would omit that, then there might be others.
If I
You gave the definition of wonderful compactification, and the theorem didn't say unique.
no, I don't think when they proved it they even knew that it was unique. So I think I don't think that's part of the original theorem.
It's unique when you have this extra.
It's unique when you, well, all of these properties are already kind of embedded into the original definition. It's just that I don't know how straightforward it is to see from I don't know, there's a lot of history, so I'm not really a specialist on who did what first, but I think the kind of standard way to understand that it's unique is to understand that it fits into a particular place in this kind of classification of spherical embeddings.
Sorry, what's the complement of the last element? I mean, the complement of J in this compactification.
The complement of G in this compactification will be like highly non-trivial, but we'll have a very nice structure. So in principle, you know, the complement is just the boundary of whatever I get when I take this embedding and I take the closure and then I remove the group. But in practice, it will be like we said earlier, it will be a normal crossings divisor with kind of interesting properties, and we're going to be able to describe it using sort of data about the group that comes from representation theory. In the same way that we constructed this compactification, actually using data about the group that comes from representation theory. Like we took a representation, we embedded it in this way. Yeah. Can you repeat the question just to make sure that I understood it? Yes. Yes. So in this, so we defined a wonderful compactification of a symmetric space associated to a group H. I tried to make some notational distinctions that were maybe useful and maybe not. So H was a group. I had this notion of symmetric space, and I had the notion of a wonderful compactification of a symmetric space of H. Sometimes, so H and a symmetric space. Sometimes H can be the product of two copies of G, and then we showed that the symmetric that there's a corresponding symmetric space that is just isomorphic to the group G itself. So G is always a symmetric space relative to kind of left and right multiplication by two copies of the group now. So now we're compactifying the group G, which I didn't need any of the symmetric space business to state this, because I used kind of representation theory of G itself. In general, if I wanted to write down a formula for like a wonderful compactification of an arbitrary symmetric space of H, then I would have to use representation theoretic data of H, and it would be more complicated. But here, this example is kind of simplified because G itself has a group structure, and its group structure is kind of closely related to the group structure of the thing that's acting. So what you can imagine here, for example, is that this entire diagram is kind of, there's an action, at least here, of G cross G. And then here, there's also an action of G cross G by just like precomposition and postcomposition with the projectivized endomorphism. And here, if I wanted to put actions on top, I would have to add tildes because I started with something that is like a finite cover of G. Yeah.
That's the case where G times G will act on that space.
Uh-huh.
Is it going to be open again? Or is what the question?
Yeah, I think, oh, I think about this. It's going to be often the case, but I don't, the ambient space can really, the ambient space is somehow not part of the data. It's just a tool that we use to construct. So if I think about the different ways that I know how to construct this compactification, like I showed you one, and one question you might ask is like, okay, well, I picked an irreducible regular representation, but obviously there are many of them in this cone. And next time we'll say more details about the fact that the variety we obtain is independent of that irreducible representation. So already we've seen not one construction, but kind of many possible constructions, one for every irrep that we can pick. And then there are also other constructions in like larger projective spaces, which we'll see probably on Thursday. In all of those cases, it's true that the ambient space itself has some equivariance. but I don't know. Is this an accident? Is it? It's in the end, the ambient space is a tool to produce the variety. So the most useful tools are the ones that are already going to have like sort of maximal relationship with the group itself.
Cedric, do we have any questions?
Yeah, there's one question from Surab Das. He asked, is there not a group scheme over the wonderful compactification which extends the trivial group scheme of the country?
What does he mean? G has a group structure, and does that group structure extend to G bar?
I'll ask him to just ask.
Yeah, of course.
Should we wait or just?
The multiplication, does it extend as a map?
No, it doesn't. It doesn't, and so this is. If I can just. We can make guesses about what the question was, and I can keep answering guesses until he comes back. So G was a group, but G bar is no longer a group, because if I try to extend multiplication in G to this boundary, it's not going to be well defined anymore. There are other questions you could ask, like the sort of group schemes naturally parametrized by G, and then you can ask, can I extend those to G bar? Those are kind of high-tech questions, but yeah.
Okay, before we thank Anna again, just a reminder that we have lunch now, and then we'll resume at 3 p.m. Thanks again.